Okay, welcome to Module 4 as we slowly add more building blocks to our frequency models. We're going to consider two issues in this lecture that we have avoided so far, but will be important for more complex frequency models down the road. The first topic is how frequency handles oxidation reduction or redox reactions. And the second topic is what to consider when choosing the right thermodynamic database for your simulation. So redox reactions involve the exchange of one or more electrons from an electron donor species to an electron acceptor species. Many such potential reactions may exist in a given system, and it's mathematically convenient to lump them as the sum of a set of redox half reactions. A half reaction contains an electron as a reactant. The half reaction for the oxidation of iron 2 to iron 3 is the example that is shown here. Redox half reactions all involve a hypothetical electron that is really a contrivance. Free-floating electrons don't exist in meaningful quantities in most solutions, and the analogy between pH and PE, where PE is the negative log of the electron concentration, isn't actually real or valid. PE is a theoretical potential, and it is used simply to help balance redox reactions so that there is never a change in the implied electron concentration, if you will, in the system. More on this in a moment. In the meantime, one other comment: the whole concept of redox equilibrium in real systems is problematic, as redox reactions are often not in equilibrium with one another. In other words, they are not all consistent with the same PE value. This is something to always bear in mind when constructing and defending a geochemical model. The redox potential of a system is a means for assuring operational valence balance, or in other words, assuring the conservation of exchangeable electrons across the entire model. Here are the rules for defining operational valence for a particular species. First, starting with an assumed operational valence of 0, subtract 1 for every hydrogen atom present in the molecule. Second, for each oxygen atom present, add 2. Third, adjust the operational valence upward or downward by the actual charge on the aqueous species, if we're discussing an aqueous species. And finally, apply rule number 3 to redox active species lacking either hydrogen or oxygen in their stoichiometry. An example of how to do this is shown for ferrous iron oxidation by oxygen here on the right. You can see by inspection that the numbers work out and the reaction balances in terms of operational valence. Using this approach, the concept of operational valence can be applied across the concentrations of all redox active species in a model. In other words, all of the potential electron donors or acceptors, be they solute, mineral, or gas. With all this as a background, recognize that frequency effectively adjusts the PE in a simulation so that the total operational valence is always conserved. That is the correct way to think about modeling redox, and not by regarding the electron term in the redox half reactions as any kind of a real entity. So let's look at an example. Consider the eventual oxidation of an unstable organic compound such as toluene in groundwater. Toluene is associated with petroleum hydrocarbon releases and leaking underground fuel tanks and so forth. Our experience and our expectation is that this oxidation will proceed through a sequence of redox reactions, starting with the most energetically favorable. This would entail oxygen or nitrate as an electron acceptor, for example, and then proceeding on to iron reduction, sulfate reduction, and finally methanogenesis. So let's set up a simulation for this in freq-C and see how it goes. Well, most conveniently, freq-C doesn't need to be told about the sequence of redox reactions here. It will figure this out on its own using its thermodynamic data. Here, we just need to specify the reaction, in this case with toluene as a reactant under a reaction keyword block over a series of steps with various mineral phases, a solid solution, and a gas phase thrown in to be evaluated. Note that the fixed volume of the gas, 0.2 liters per 1 liter of water, is intended to represent gas-filled pore space within a porous medium. Also, the NTG component of the gas phase is actually non-reactive atmospheric nitrogen, which makes up the bulk of the gas phase at the start of the problem. So the one cheat that we've included in this model is an alteration of the equilibrium constant for ammonium, and this is under the solution species keyword block right below the title on the input file. This was done to prevent reduction of nitrate all the way to ammonia, as opposed to stopping at nitrogen gas, which is actually what happens typically in reality. A more proper alternative would be to model nitrogen redox reactions kinetically. More on that in another module. But the modification used here allows us to stick with the redox equilibrium model as a demonstration. Again, there are always choices to be made with FreakC as to which assumption can be justified for a given purpose. Here are some summaries of the model results for the aqueous phase, mineral phases, and the gas phase. All shown as a function of the amount of toluene mineralized all the way to CO2. The results are pretty much what you would expect based on experience if you are a contaminant hydrologist. We see, for example, the rapid depletion of oxygen both in the aqueous phase and in the gas phase. And this is followed by denitrification and the evolution of nitrogen gas into the gas phase. This is followed in turn by partial reductive dissolution of ferric hydroxide along with sulfate reduction. And these two lead to the precipitation of an iron sulfide phase, and we also see the development of a ferro calcite that's soaking up some of the additional ferrous iron that's generated in the problem. And finally, we end up at a state of essentially methanogenesis, where we're creating methane from the toluene, and the methane is evolving into the pore space gas. This all makes sense and is consistent with expectation. So we're going to switch gears completely at this point onto another topic, and so let's discuss databases. FreakC comes with several, with the following being the major ones you will probably use the most. The first is freakc.dat. This is the default database. It has some surface complexation data as well as cation exchange equilibrium constants in it as well. We'll discuss these a bit later in another module. The LLNL.dat database, this is a very large database with many components and minerals, and uses the extended Debye-Huckel model for calculating activity coefficients. The Mintec database, this data set contains a lot of aqueous phase complexation reactions for metals and organic species. The Pitzer database. This database is designed to handle brines with a specific ion interaction model. However, it lacks data for iron and aluminum and redox reactions. And finally, the SIT.dat database. This is based on a simplified, limited version of the specific ion interaction model. So it may be applicable to more concentrated solutions in some situations. It includes many more elements and minerals than does the Pitzer database. So let's briefly touch on a couple of examples that illustrate the impacts of selecting different databases for your models. The first example is an illustration of how some of the complexation data featured in the Mintec database can provide insights that other databases cannot for certain special problems. Here we have a simple sodium chloride water that is initially in equilibrium with aluminum hydroxide and iron hydroxide. We're going to add citrate to it. Citrate can strongly complex with a variety of metals, including iron and aluminum. It is not represented in the LLNL database, for example, so this simulation needs to be run under that database without citrate, essentially as a control with which to compare the Mintec generated results. Here are those results. Citrate very strongly complexes with both metals, according to the Mintec database, significantly increasing their solubilities by over 2 orders of magnitude in the case of aluminum. This is despite the final pH being higher in the Mintec informed model with citrate than the LL informed model. Okay, so here is a different database problem, in this case one that takes into account different activity correction approaches. This is a simulated evaporation problem with H2O removed from solution via a reaction keyword block, effectively concentrating the remaining aqueous solution. The simulation was run with 3 different activity correction modeling approaches from 3 different databases, the Pitzer database, the SIT database, and the LLNL database, all compared. The simulated precipitation of mineral phases common across the 3 databases was also included here. So the 3 different databases generated moderately different ion concentrations at high solution concentrations. The Pitzer model should be regarded as probably the most accurate given its optimization for these types of problems. Some differences in the amounts of different common evaporite minerals precipitated among the 3 databases is also evident. As an additional note and a plug, if you will, for using the Pitzer database for problems involving brines, I'll point out that there are a fair number of soluble minerals included in the list of possible phases under this database that are not included in the others. This may provide some useful additional flexibility for certain problems. So looking back over this module, try computing the operational valence balance for some of the steps in the sequential toluene oxidation model. If the simulation is correct, the sum of the operational valences across all the constituents in the model, including toluene, the aqueous species, solids, and gases, should be conserved.